You should be able to.
Got it. Okay. So I'm going to be speaking on small hive beetle biology and control, and I'm also going to be sharing some of my research that I've done in collaboration with the University of Florida and the USDA on honeybee or hive beetle treatments. So before I get into my actual research and presentation, I'd like to begin with my background of how I really got into honeybees at a young age. So 4 years ago, I went on a short fishing trip with a friend and his grandfather. And actually, while we were on the boat, my friend's grandfather, who was about 80 years old, started telling us some stories about his beekeeping practices and about how decades ago he would get dozens of barrels of honey. And now that season, he got nearly 3. So this is very shocking to me at the time. And after getting back home, I really dug into the research and the statistics, and I did some brainstorming. And I really came to realize the importance of honeybees and the severe decline that they have endured, particularly in the United States throughout the last few decades. So for the last 4 years, I've been working on extensive honeybee conservation research since the 7th grade. This image on the top right is actually a picture of me from my 6th grade summer working in the UF lab. That year was very comfortable for me. I was in the laboratory, it's air conditioned, it's a very comfy and cozy environment, contrary to the field setting where it's very hot and you have to lift these heavy supers full of honey. So in years after my first year of research, I really came to understand the value and the hardship that goes into beekeeping and how difficult it really is to put food onto our plates. So for the presentation for tonight, it'll be broken down principally into 2 things: the biology of the beetle, being the background, morphological characteristics, and behavioral and social characteristics. And then the second aspect of this presentation will cover treatments. And this will be twofold: chemical-based treatments and then also organic-based agents. The research that I conducted and what I'll be sharing with you was on organic-based treatment agents for the hive beetle. Some takeaways I'd like you to have by the end of this presentation are: firstly, what small hive beetles actually are; secondly, what small hive beetles do inside honeybee colonies and what they actually do to the bees, how they affect them; third, I'd like you to know what I actually discovered from my research; and lastly, I'd like you to be able to know how you can apply my findings in your hobbyist or your commercial beekeeping practices. So let's get into it. Athena timida, which is a scientific name for the small hive beetle, is endemic or was endemic to sub-Saharan Africa prior to the 2000s. However, in the late 1990s, it actually started spreading, and the first reports came from the Carolinas in 1996. The first actual infestation was reported in our state, Florida, in 1998. And since then, these beetles have spread all across the globe. As you may know, in the United States, we have a very large migratory beekeeping operation where nearly 2/3 of our hives go to California for pollination of almonds each year. So it's a frenzy for all of these pests, parasites, and diseases. And essentially, if one hive has something, then the other hive will definitely catch it. And diseases and pests can spread very, very quickly. And this is what we were seeing with hive beetles as well. So this pest is spread all across the globe, and it's wreaked significant negative impacts on the beekeeping industry. These beetles are often described in the literature as opportunistic scavengers, and they're very, very smart with how they reproduce, which I'll be discussing in further slides. But how they actually affect the colony is by destroying the honey and the pollen stores and damaging cappings and comb, which ultimately stresses the colony, and in fact can lead to the bees absconding entirely from the hive. And so absconding is when the bees will just pick up all their things and leave entirely, leaving the hive just empty, essentially. Now, this is the case with the European honeybees, the ones that we manage in North America particularly. However, these small hive beetles, which are endemic to sub-Saharan Africa, where the Africanized honeybee is located, in particular with the African honeybee, these small hive beetles weren't really a threat to that species, but we're really seeing it impacting the European honeybee or the Western honeybee. Now, this is the, one of these is a male and one of these is a female on the right. So you can actually sex these beetles by squeezing on their abdomen, and one of 3 things may happen. The first thing that can happen is that a short appendage will shoot out. The second thing is that a long appendage will shoot out. And the third thing that can happen is that the beetle will simply explode if you press too hard. And that has happened to me with my research, squeezing too hard when you're trying to sex these beetles. But when you squeeze the beetle and a long appendage shoot out, you may be inclined to think that that's a male, but that's actually not a phallus. It is a female. And so that appendage is actually an ovipositor, and it functions as essentially an egg-laying machine gun. So what the female can do with that ovipositor is stick it into cracks and crevices within the hive and deposit eggs. in these places where honeybees can actually access them and remove the eggs from the hive itself, which makes it very convenient for these beetles to reproduce. And the image here on the bottom right, this left image, the short appendage is actually the male. You can see that here. Now, on the left, these are two other beetles that can show up in your colonies. This is a pollen beetle and a sap beetle. Now, these beetles, although they do look somewhat similar at first glance to the small hive beetle, are very different from the small hive beetle and don't cause the same damage. Now, I show this to say that just because you see other forms of beetles or other species inside your hives, it doesn't necessarily mean that they're hive beetles, and it's not a call for concern. The best thing to do is simply compare these beetle species against small hive beetles, either images, or call your local bee inspector to confirm which one is which. Now, this image on the right here is actually a large hive beetle. They're called large hive beetles because they're large in size, 20 to 23 millimeters in length for this large hive beetle. Now, the large hive beetle doesn't refer specifically to a singular species of beetles, but rather each region has their own assortment of large hive beetles. Now, the small hive beetle gets its name because it's small in comparison to this large hive beetle. Small hive beetles are 4 to 6 millimeters in length. And so they're obviously 4 or 5 times smaller than this large hive beetle. Now, I'd like to discuss the life cycle for the small hive beetle. Now, there's 4 primary stages in the life cycle of this beetle. The first of which is the egg stage. The second of which is the larval stage. And so after these eggs hatch in 2 to 4 days, they emerge as larvae. And these larvae are really the main cause of the problem for small hive beetles inside the colony. As I mentioned earlier, what these larvae do is really crawl through the comb and the honey, and they basically defecate inside the hive, which I'll discuss further in the next slide. So they are the main cause of the problem. And after they feed an ample amount, they will exit the hive and then crawl into the soil and pupate there, where they mature for 3 to 6 weeks. After that 3 to 6 week period, they emerge as adults and develop this reddish brown hue in the next 24 to 48 hours inside the colony. So that's the complete life cycle. Now, doing some very quick math here, you can see 2 days, 7 days plus 3 weeks. This is the time it would take for the beetle to fully develop from this egg stage to this adult stage in optimal conditions. So 2 days plus 7 days is about a week, give or take, plus this third week is about 4 weeks. So 4 weeks from that egg stage to this adult stage, especially in Florida where we have moist soils with the sand and a high humidity. This beetle tends to do very well in Florida and all southern states and in the southern hemisphere itself. So this 4-week time period, looking at the life cycle of this beetle, which is 24 weeks, 4 times 6 is 24, meaning that we can see up to 6 consecutive generations of these hive beetles inside a hive, given these optimal conditions. And I say this to say that these beetle infestations can get completely out of hand if they're not controlled. Now, the larvae are the root cause for the damage, as I said. You can see this image in the middle here is a very bad infestation. So these larvae appear very suddenly and in large numbers, often in the hundreds or the thousands. An interesting thing to note here is that there's this yeast associated with the feces of these larvae that actually causes the fermentation of the pollen and the honey. So this yeast is called Codima omeri, K. omeri, and it's here in the bottom left. So when this yeast interacts with the sugar and the pollen and the honey, particularly the honey, it causes the fermentation, and this fermentation releases a chemical compound, which is actually the honeybee alarm pheromone, one of them, isoamyl acetate. So what isoamyl acetate does when it's released is it essentially serves as a calling signal to small hive beetles in the vicinity of that hive and tells them that there's a surplus of food here and that there's an infestation. Now, when this event occurs, this slime out, quote unquote, and these larvae are they've taken over the hive essentially, then the population will dwindle and the brood rearing will cease entirely. The bees may also abscond or leave the hive. There's really 2 telltale signs of a very bad larval infestation. The first of which being that when you pop open the super on the top of a hive, you will smell a rotting citrus odor. And the second thing is that you will see honey actually bleeding out from the front of the colony, as you can see in this bottom right image. An interesting behavioral characteristic I'd like to note here is something called the jailing phenomenon. Now, that's not an official scientific term, but that's just what I like to call it and what it's sometimes referred to as. Essentially, this is where these small hive beetle are actually cornered into cracks and crevices within the hive. And the beetles will actually corner them there and keep them there, sort of as a jailing mechanism to keep them in place. Now, 10% of the time, an interesting thing will happen. These beetles will actually take their antennae and antenate against the mandibles of the honeybee. And this actually causes the honeybee to regurgitate food to the hive beetle. So the honeybee is essentially feeding the hive beetle here. And this happens 10% of the time, where the beetle is able to trick the honeybee into feeding itself. The other 90% of the time, however, the bee is smart enough to pick up that it's not a honeybee, and this phenomenon won't occur. Just something interesting to note. And that really shows how smart this predator can be. Something else I'd like to mention is the comparison between the wax moth larvae and small hive beetle larvae, because at first glance, they do look a bit similar. One of the biggest characteristics, obviously, is the webbing and cocooning you see with these wax moth larvae inside the hive. Another big characteristic, and literally, is that these wax moth larvae are a lot bigger than small hive beetles. They're nearly twice in length and 4 times in width. Another thing to note is these hairs that are all across the wax moth larvae's body. The other thing is these legs. So the wax moth has 8 prolegs and 6 legs near the head, whereas the small hive beetle only has 6 legs near the head. The small hive beetle also does not have any hairs, and it has much more pronounced abdominal segmentation, as you can see here. Now, just some good notes for managing small hive beetle infestations in your hives. First thing is, when combining or exchanging comb, you must be careful, because you can actually introduce small hive beetle's eggs from outside the colony into a new colony, which may not have a small hive beetle infestation. Another thing is that when removing old frames or hives, you should be very careful, and even adding old frames or new supers, because dilapidated, such as rotten, cracked, or damaged comb, can make for very good hiding spots for beetles, and this ultimately allows them to deposit their eggs inside these spots, which the bees can't get to remove. So it's giving them a good shot at reproduction. Another thing, the biggest thing probably, is that when pulling honey from your colonies, it's very important to extract quickly, preferably within the 2-day mark, because the beetles will actually consume the wax cappings and start defecating inside the honey, which renders it unsuitable for consumption. Another easy thing to do to manage for these infestations is just simply exposing your hives to sunlight. And so what this does is that the hive beetles don't like sunlight, they're not fond of it. However, the honeybees don't mind as much. The bees will get a little bit aggravated, but it's a very good way to control for hive beetles without doing much. Now, for nukes, or even adding new supers on top of existing supers, or adding new frames, it's important to only add as much as the hive is progressing with, essentially. So if you have a weak colony and you added a super on top of it when it really didn't need it, this would make for a very good spot for beetles to roam freely, rather than these bees trying to patrol them. So this is particularly a case with those weaker colonies which don't have bees to monitor the entire hive. Now, I'd like to transition into the second segment of this presentation, which is the treatments. Now, first, I'd like to begin with chemical treatments. 2 big chemical treatments in the industry are probably checkmate strips, which have a 10% active chromophos ingredient in them. And so these can be used for varroa mite infestations and also small hive beetle infestations inside colonies. It's applied as a strip. Guard Star, which has 40% permethrin, is applied as a soil drench in the vicinity of the hive. And you may have used these treatments or heard about them, as they're pretty popular. Now, these are the stages of the life cycle of the beetle. The chromophos strips are applied during stages 1 and 2 when the beetle is an adult. The beetle will come in contact with the strip. So for hive beetles, it's attached to a piece of cardboard, the chromophos strip. You staple it onto there and put it on top of the frames. And when the beetle interacts with the chromophos on that strip, it will die. Now, the permethrin is applied during the pupation stage of the hive beetle, or stage 5 here, when it pupates in the soil, and it will simply kill the beetle then. Moving on to non-chemical or organic and biological treatment agents, there are quite a few of these agents that exist on the market. One of the biggest ones probably is the use of these quote unquote attractants, which are placed inside traps. And this is actually what I researched, and I'll be sharing this later. But these attractants are essentially odorous compounds that can be placed inside these traps. And how they function is that they lure beetles that are already inside that hive into this trap because of their odor. So these beetles will enter through the slits on the top of these traps, and then they'll fall in and drown in that solution. This is a baseboard trap you can see here, another popular trap that's used for these hive beetles inside the hive. Diatomaceous earth, this third image. So this is placed in the vicinity of the hive, and it dries out the cuticle of the insect, the small hive beetle, which kills it eventually. This last image on the right here is one of a nematode. So this in particular is a class of nematodes called entomopathogenic nematodes. And how these nematodes function is essentially they kill the insect from the inside. There are many different species of nematodes. This one in particular is for small hive beetles. How it functions is essentially enters through an orifice of the hive beetle, either to the mouth or the anus, and then travels through the gut where it feeds on the hive beetle and kills it from the inside, so it's a parasite. Now, moving on to my research. There are many chemical treatment methods that exist on the market. There are also advantages and disadvantages of these chemical agents. What I was looking at in my research was organic-based treatment solutions for small hive beetle treatment. So I'd like to go over this briefly. Some advantages of using these pre-existing chemical treatment methods are, first, that they're highly effective, and secondly, that they show fast results. However, there are a myriad of disadvantages with these chemical treatments, the first of which being that they can become unaffordable, especially on a large scale. Another thing is the risk of soil, water, and environmental contamination. This Comophos in particular has been shown to have a half-life of less than 30 days in water with no light, and up to a year in soil. So it can last in the environment for a very long period of time. And this ultimately affects wildlife, aquatic life, and not to mention the honeybees themselves, which is where you're placing this strip inside the hive and trying to save them. It's ultimately having adverse effects on the honeybees as well. Not to mention that chemical residues have also been found in various hive products such as wax, propolis, royal jelly, comb, honey itself. So these are ultimately things that us humans use. Honey, for example, is just straight consumption, but other products in the pharmaceutical and beauty industries. So these are ultimately going into or onto our bodies and have adverse effects on our health as well. The proposed organic treatment solution that we were looking at is something that is affordable and sustainable, but also effective for small hive beetle capture, environmentally friendly, naturally biodegradable, and poses no adverse health risks to humans, wildlife, aquatic organisms, or the honeybees themselves. So what is this research? This is broken down into two phases, year 1 and year 2. The first year was looking at 7 different organic and inexpensive small hive beetle treatments in a field trial. And the second year was looking at developing a novel treatment method based on beer, which was actually found to be the most effective agent by far in this first year study. So phase 1 was finding an organic agent, and phase 2 was developing a synthetic agent based on beer from year 1. That was even better than beer. Now, beginning with phase 1, here we were looking at 7 organic agents. So these were apple cider vinegar, which was the positive control of the study. It was the standard essentially, as it's used by many beekeepers and is pretty popular. Mango puree with boric acid, cantaloupe puree with boric acid. I should mention that both of these fruit treatments had a 2% boric acid concentration, yeast, baker's yeast, peanut oil, grapeseed oil, and beer. So these 7 treatments were used because they are odorous compounds essentially. And so literature has shown that the beetle, this beetle in particular, which belongs to a class of coleoptera known as Didodulidae, have been shown to fundamentally feed and reproduce on tree sap, rotting fruits, and other such odorous compounds. And so based on this, these specific compounds were chosen. Now, these compounds are placed in these beetle blaster traps, which this is actually the 6-inch trap. I have one here as well. And so these are the mini ones. These slits are small enough so that only the beetle can enter through here and the bee cannot. These are filled to about halfway with 10 to 12 milliliters of treatment solution. This image on the bottom right shows these black specks, which are actually hive beetles that have been captured, and that's cantaloupe. Now, this is the research, some pictures from the research that I did, and I believe this is 2020 during the pandemic. So I'll get to that. I have a funny story about that. On the left, this is me in the field working with the bees. You might be thinking, what a responsible young beekeeper with his beekeeping equipment and his gloves on, but that's not true. That's a wrong statement. In fact, I got stung dozens of times while in the field. It was not an exhilarating experience for me, and it was very painful, but it really came to teach me to appreciate like how hard beekeeping can be sometimes. And can you really call yourself a beekeeper if you haven't been stung that many times? I mean, I lost count. It was in the dozens. This image in the middle here was during the pandemic when I didn't have access to any laboratory, so I had to work at home. I was counting beetles in my mother's kitchen, and she wasn't all that fond of this idea. Beetles would often get loose in our house. So we'd have to take fishnets in hand, my brother and I remember this, and try and catch these beetles. We still may have beetle larvae in our house to this day, we'll never know. And this image on the bottom right is actually a trap which has beer in it. So all of these black specks are beetles that have been captured in it. And how this trial essentially worked is that the treatment solution would be placed inside these traps. And this trial was run across 24 different honeybee colonies for a 6-week period in the fall. Each week, these traps would be placed inside the hives and then extracted the next week and replaced. So this was essentially an extraction and replacement for 6 weeks with data collection weekly. And so these beetle counts were tabulated and then analyzed statistically. And so I don't want to dive too much into the statistics, but basically what's happening here in this test on the left is apple cider, which was the control, is being compared against these different treatments. So apple cider is being compared against mango mix, cantaloupe, yeast, peanut oil, etc. Apple cider versus all of the other treatments. And the reason this is being done is because apple cider was the positive control being compared against the other treatments that were essentially experimental. Now, what's important to note here is that these columns which have these orange arrows are the treatments that were significant in comparison to apple cider. So mango mix was doing better than apple cider throughout the course of this 6 weeks. Cantaloupe was also doing better, yeast was doing better, and beer was doing better. So these 4 treatments were better than apple cider in this study. Another series of statistical tests was used to find out which specific treatment was the best by far of all the agents. And so this treatment was shown to be beer by far. Looking at this graphically and moving away from all of those numbers, this is the Pareto chart. And so you can see the individual bars here, which represent the raw beetle capture for each of the treatments. Here in dark blue is beer with a total capture of 198. You can see this Pareto chart has an 80-20 rule. So this 80-20 rule essentially states that when you trace vertically or horizontally here from this 80% mark, and then trace down, that the segment on the left of this vertical line, essentially beer, cantaloupe mix, and part of peanut oil, 20% of what is inside this red circle, 20% of that makes up for 80% of all of the beetles captured throughout the course of this study. So I'd like to reiterate that. 20% of what is inside this circle accounts for 80% of all of the beetles captured throughout the course of this study. And so that's a very powerful statement because this really shows you the efficacy of beer, cantaloupe, and to some extent peanut oil throughout the course of this study compared to the other treatments. And so you can really see this graphically here. The box and whisker plot, what I'd like you to pay attention to, please, is this X here in the circle. So this X represents the mean. And so this mean is representative of the consistency and efficacy of the beetle capture for this treatment throughout the course of the entire 6-week period. This X is much higher than any of the other treatments in this study. And so that really shows that beer was more consistent and more effective throughout the course of the 6-week period. Now, what did we ultimately conclude from this year 1 trial? So this year 1 trial showed that beer was 33 times more effective in its beetle capture than apple cider vinegar, which is one of the most popular treatments used by beekeepers for small hive beetle capture. This beer costs merely 5 cents per hive on average, and it's also widely and readily available. In addition to this, beer does not harm the bees and only beetles. So you will not end up with any drunk bees inside the hives, I assure you. So this treatment is actually placed inside the hive between the frames. And so it doesn't have any chance of toppling unless the entire super topples. If you didn't believe me on that economic comparison, this is an image from Walmart.com. Miller High Life is the beer that was used in this study. And this is an image of apple cider. So you can see here that Miller High Life is merely 7.3 cents per fluid ounce, compared to apple cider vinegar, which is nearly 20 cents. So Miller High Life is 3 times cheaper than apple cider and 33 times more effective. I'd like to have a moment to let you think about that really. So it's a lot more effective and also a lot cheaper. Now, for phase 2, which was year 2 of the trial, this was where we were looking at developing a novel blend based on beer's chemical composition. So as you may know, beer has a 90 to 95% constituency of water. It's very diluted. And so the goal here was essentially to concentrate beer with specific compounds and make it refined so that it could be a more concentrated solution of beer. The goals for this study were to make a solution, a beer-based blend that was even cheaper and more effective than beer itself. So how did we go about actually doing this? The first step in this process was extracting the chemical compounds from beer itself. So here you might be able to see I'm holding a white rod in my hand. It's a filament and it's called a polymer. So this polymer is attached to this vacuum tube here, you can see. This clear tube, when it's turned on, and that's the vacuum here, this black box, when it's turned on, the chemicals from this beer bottle are actually trapped inside the polymer here. And so this polymer has a chemical structure that's specifically situated to trap those chemical compounds. And those chemicals are known as volatiles. So those volatiles are essentially taken from that beer matrix and then trapped inside that filament, that white tube. That white tube was then placed inside this machine you can see here in the middle and then analyzed. So the first step was taking chemicals from the beer, and the second step was analyzing what these chemicals actually were. What this instrument does, and the instrument is called a GCMS, it's a gas chromatography mass spectrum. So that's a mouthful, but that's not important. Basically what this instrument does is it analyzes the chemical composition of the sample based on the molecular weight of the compounds. And so there's this very long coil inside this machine, and this filament is heated to a very high temperature, which causes these chemicals to be released and introduced inside that coil. As time goes on, and this coil is 10 meters to 100 meters in length, it's very long. As time goes on, the chemicals from that filament begin to separate inside this very long coil, and then they reach a detector at the end of the coil. So the heavier molecules actually go slower inside that coil, and the lighter ones travel faster. So it's the lighter molecules that are picked up on that detector at the end of the coil. And that's important because this instrument produces a reading. As you can see here on the right, this is a sample reading. The x-axis here is the time. So as you get closer to the left here, this is the quicker these chemicals were picked up. And it was really these peaks on the left of this spectrum that were of interest because these were the chemicals that are lighter in molecular weight. And so if any of that didn't make sense, basically these chemicals that are lighter in their weight and are shown at the left of this spectrum here are carried more easily in the air. And this is important because these compounds are thus more easily picked up by the beetle. The heavier chemical compounds sit in the air and they're not as easily carried. I know we have less than a minute.
Yeah, I just want to let you know, just in case. I can start a new Zoom link if there's more to your presentation, and I can send that.
Yeah, I have a few more slides. I think that'd be great if we could do that.
Perfect. I'm gonna go ahead and close this off and send you a new link.
Sure, thank you.
Thank you.
Okay, so this spectrum is important basically because these compounds that are on the left here weigh much less than the compounds on the right. So these compounds that weigh less are carried more easily in the air, and thus they're picked up by the beetle first. Because the goal here was ultimately to develop something that would be attractive to the beetle. And the thing that would reach the beetle first is these lighter compounds. And so they were a focus of this study, really. Now, specific compounds were identified from this spectrum, and then they were tested in the form of this setup here called an EAG, or electroantenography, another big word. But basically what's happening here is a few things. One of the biggest things that's happening here is basically antennal testing of the hive beetle. So basically, these beetles are 4 to 6 millimeters in length, by the way. And so trying to excise their antennae, which are a few hundred micrometers in length, was very difficult. They had to be squeezed with a set of tweezers and then put under a microscope, and then their antennae were excised. So this was a very, very tricky process, almost like neurosurgery, but on hive beetles. Now, after those antennae are excised from the beetles, they're actually live from anywhere to 3 to 5 minutes. And so time is really of the essence in this process. After excising those antennae, they're placed onto a forked electrode that's shaped like a V almost, and then they're placed here this way. Now, once they're placed, you can see this arrow on the top left here. That's where the antenna is. There's this filter paper that's been dipped inside a isolated volatile compound. So one specific compound is being tested at a time with this setup. And so this filter paper is dipped inside the compound and then placed here. This is connected to a foot pedal, this tube. When that foot pedal is pressed, air is pushed through the tube, and then that air interacts with this filter paper, which then is exposed. It carries that chemical, basically the air, and that air with the chemical then interacts with this antenna. So then the antenna picks up a response, just how the beetle would, except what you can do is you can see how the antenna is responding via this electrode. So what this electrode does is it transmits the signals from this antenna through to a personal computer where you can analyze the readings as either positive or negative and see how the beetle is responding to it really. And so this is useful to see which compounds are actually viable for being put inside a blend. After that process, a total of 2 blends were created from the laboratory. There was an oil-based blend and then a water-based blend. In addition to this, there was a control that was tested, a oil, and then also apple cider vinegar. Now, also beer, excuse me. So beer was tested in comparison to this blend to see what the efficacy difference would be between them. So there were a total of 4 treatments. And so this image on the right here is of the blend, and all these black specks here are actually hive beetles. So you can see how effective this treatment really is inside the hive. Now, after this process, and the process for this field trial where these treatments were placed inside the hives was the same as the year before, except this was replicated at 3 different apiary sites across Florida, 2 in Bartow, and then 1 in Gainesville. And then this is run for an 8-week period. So the period was extended and the sample size was also larger to ensure that this would be an accurate data set. And then after the extensive data collection for that 8-week period, a plethora of statistical tests were also run on the data. And ultimately, the oil blend was shown to be the most effective treatment by far. Moving away from these numbers, we can look at this graphically again. So the oil blend is in gray here. The oil water blend, which is the second blend created, is blue, and beer is here. The control is here. We can also observe the 80-20 rule as we discussed previously with this graph. Looking here at the 80% mark and tracing horizontally, then tracing down, we can see the oil blend and almost half of the water blend. So again, that segment on the left here, 20% of that segment makes up for 80% of all of the beetles captured in this study. Again, 20% of that is 80% of everything. So it really goes to show the efficacy of this oil blend. You can also just see the raw beetle capture here, which is 620, 629, so on and so forth for each of these treatments, and compare that. Now, ultimately, the conclusions from this year 2 trial were that the oil blend treatment was extremely effective by a far margin. This oil blend was shown to be 5 times more effective than beer, which is already extremely effective and also half as expensive as beer. Now, I'd like to speak about how you can actually use these findings and why you should use them. So first off, again, beer does not harm your bees. You will not end up with any drunk bees inside your hives off of beer. Beer can be used as an in-hive attractant for any different type of in-hive trap. So anything that requires an attractant-based trapping solution, beer can be used there. Beer is also extremely cost effective, as I mentioned earlier, 7.3 cents versus 20 cents for apple cider vinegar, which is commonly used. So it's a third of the cost essentially. Now, the key takeaways for small hive beetle management are essentially 2 things. First of which is having good apiary practices, maintaining cleanliness, giving your hive sunlight exposure, keeping your frames clean, not using old frames that have cracks and crevices within them. The second thing is using treatments, whether that be ultimately up to you, chemical or organic-based treatment solutions to control for hive beetle infestations. And in the end, ultimately, it's a synergy of these 2 things that reduces beetle populations to a low and manageable level inside the hive. So these are some resources for small hive beetle management that I can definitely share with Miranda if she'd like to circulate this amongst you all, but these are some helpful things. These first two links are PDFs to some things and facts about small hive beetles, their management and their biology. This last link is a link to the UF Honeybee Lab page, which contains a lot of helpful videos, not just on hive beetles, but just in general for beekeeping practices. And so that's all I have for you today. Thank you so much for your time and attention, and I hope you found that informative.
That was awesome. Thank you so much for sharing your research, and we hope to have you again here in the future at our meetings. That was great. Thank you for your time.
Thank you so much. I'm open to questions now, if anybody has any.
I think the biggest question I have, how many hives were used in the study for year 1 and year 2?
Did you hear her?
Yes, yes. Yeah, thank you. So there were 24 hives that were used in the first year study, and then a sample size of 28 colonies was used for the second year. So 24 and 28.
And did they use different treatments in the same hive?
Yes. So yeah, so there was randomization of these treatments because essentially you would have bias if, let's say, there's hive A that has 10 beetles and then hive B which has 100 beetles, and then you're consistently putting different, like, so you have one treatment that's going into this hive with 10 beetles and then another that's going in the hive with 100 beetles. The treatment that goes in the hive with 100 beetles is obviously going to have a much greater capture. So to adjust for this, there was randomization. So the week after, these treatments would all be swapped. And you could argue that the beetles from that hive with 100 beetles might be reduced the population of that hive. But this really can't be controlled. And since it's run at such a large scale with this randomization, it tends to cancel itself out, especially with these stats, which look at these outliers within the data. And so that was really used both years, an extensive stats analysis to really confirm if there were any outliers or biases within the data set.
Do you have a question? Oh, go ahead.
How many hives were in the second year?
Yes, it's 28.
Okay.
For beer, he only used one, right? He did a beer is beer, not test to see if they like better beer than
Sorry, I didn't hear that question quite clearly.
no.
He was asking if you use one beer, correct? I would like that.
Or-
Yes, yes. So Miller High Life was used. That was a brand of beer, and that was actually chosen because it was just inexpensive and readily available. What a lot of people have told me about is doing perhaps a beer comparison study, so looking at different brands of beer. And it's actually funny that you mentioned that and have a question about that, because I have a brother, coincidentally, and you might guess what he's doing this year. So he's doing a beer comparison study where he's actually looking at different brands of beer with hive beetles and seeing which brand of beer is actually the best. And amongst those brands, there's 8 of them. Miller High Life is a contestant. So that's an ongoing study, and we'll see what happens. I'd be happy to inform you all about the results of that project.
I'd love to hear the results.
Interesting. I know the guy in the back, you had a question, right?
Yeah, I'm just curious about the oil-based solution. Yeah, if like what you use to make it, or is that available to the public?
Right. So at this stage, unfortunately, that blend is going through a patent process. So I'm not exactly sure when that blend would be available, but the goal is to make that blend extremely affordable. So for now, you can't really create that at home. There's different chemicals that have to be mixed, and then a concentration has to be used. So that would really be something that would have to be created in the laboratory. But the best thing that you could use for now is probably just plain old beer. And again, what I use is Miller High Life. But the goal is to try and bring that to a commercial scale where it could be extremely affordable.
Any other questions?
Thank you for sharing.
Thank you. We really appreciate you being here.
Of course, I had a great time. One request I do have for all of you in attendance tonight is just if you could pull out your phones, please, and open it up to the camera app and scan this QR code. This will actually open you up to a form. And this is just basically asking, it's 2 questions about what you thought about my presentation and my speaking abilities. So this is really great for feedback, and it lets me know how to adjust for any future presentations or interactions. So I'd really appreciate if you could take a minute or two to fill this out. It'd be a great help. So thank you.
If that is the same form you have linked, I'll post that inside.
Okay, sounds good. All right, well, thank you so much. And we'll hope to see you again in the future, and good luck with any other research that you'll be doing.
Thank you. I had a great time.
Okay, all right, so to end off this meeting, we have, I'm gonna take you off like this real quick.
Okay. A good night to all of you.
Good
Bye.
night. Have a good night. Oh, I think you have to take yourself off as host.
Oh yeah, I'm gonna make you host.